Hi everybody, I hope you're doing well. In the previous lecture, we discussed in general the second quantization of operators acting on two particle coordinates. Okay, so two particle operators. And of them all, perhaps the Coulomb interaction between identical particles is one of the most important aspects for elementary particles in solid state theory. And to do that, we first will present a review of basic aspects of the Coulomb interaction, and then we second quantize the interaction using plane waves, which is a very interesting problem. Okay, so let us first review basic aspects. Of course, we are trying to consider here the instantaneous Coulomb interaction between two charged particles, and therefore it is classically described by electrostatics. Okay, so electrostatics in general, it is the subject which discusses the Coulomb interaction and at a simple level. Okay, so electrostatics is described by something like this. Okay, a Laplacian of a potential field, which is a function just of the position. It could be a function of perhaps of time, if not electrostatics. But in electrostatics, we have the following. So the Laplacian of the field phi, depending on r, is equal to minus the charge distribution. Usually it is written as a rho, a function of the position, divided by epsilon. This phi is the so-called electric potential or electrostatic potential. It is measured in volts in the International System of Units. Rho is the volumetric charge density. And in the using the International System units, it is measured in coulombs per cubic meter, while epsilon is the so-called dielectric permittivity. Of a medium. In international system, it is measured in farads per meter. Okay, so this is what describes the potential produced by charge distribution. Okay, so we will introduce a slight variation of this equation by introducing a term which is proportional to the potential. It will produce the so-called screen Coulomb potential or electrostatic potential, okay, for a point-like charge. Well, if you have two, we will solve this equation. But if you have two particles of the same charge in classical electromagnetism, in classical electrostatics, the potential energy is given by the following. So the electrostatic potential energy, it is given by some U depending on the two charges, but they are the same here. So of two distinct charges, perhaps it is written as charge Q, charge Q primed, divided by 4 pi epsilon, which we will consider for the sake of simplicity to be the vacuum. Okay, so, or it can be of any given medium, and the distance r minus r primed in modulus. Okay, if you have in a given coordinate system charge q and charge q primed, they are located at r and r primed. The distance between them is given by this vector r minus r primed. It points from here. Okay, so it doesn't matter because it's modulus which enters the potential. It is a scalar function. So if you have a set of particles in classical electromagnetism, the total energy of a set of particles, okay, what you really have is the following: a potential energy which corresponds to the total sum of interactions between pairs. So you have the key Qy and Qi and Qj. There are two distinct particles with distinct charges. We will specify using just the same charges in a few moments, the identical particles, so these charges will be the same, all right? So divided by 4 pi the epsilon of the medium, the electric permittivity here of the medium, and the modulus of the distance between these two I and j particles, okay? You sum over all the I and all the j's, all i's, all j's, but then you'll count twice the potential energy, and therefore you divide it by 2 if you not specify that some connection between these indices here. If you are to sum over all the i's and all the j's indices here, you will count twice because at some moment I is equal to 1, j is equal to 2, and in the summation you'll find out I equal to 2, j equals to 1, but this produces the same value, and you count twice. So if you don't put any constraint, the only constraint is I is distinct from j because it would correspond to a divergence of this equation, and it would correspond to the interaction of a particle with itself. Okay, it's a very important problem, but in this case you are counting the energies of the interactions between distinct particles. Okay, and you will not count twice. You need not count twice the energies. You divide it by 2. It is just because when, as an example, when I equals to 2, j equals to 1, you have R2 minus R1 and the product of the charges. This is modulus. And when I equals to 1, j equals to 2, you will have the same modulus, the same energy. You need to count the energy of the particles just once. But if you do not imply any rule here, the only rule is I distinct from j. They must be unequal. Okay, you need to divide it by 2. So this is for electrostatics of charged particles. And of course, a point-like charge, the charge density of a point-like, for a point-like charge, the density will be the charge of the particle and the Dirac delta at the position of that particle. So for the J particle, the density will be given by Qj r minus the position of that particle. In d dimensions, usually 3 dimensions. So charge density, it is infinite in a point-like particle because there is a charge there in a volume which tends to zero, and otherwise it is zero. Okay, so this is well represented by Dirac delta function. Okay, for point-like particles, the charge densities can be written this way. So this equation here, it could be written in the following way. Suppose you define a row of summation of all the position of the particles. So a row of R, it is equal to the summation over all the J's, Qj, and the Dirac deltas of R minus Rj. You could rewrite this equation here in the following way. U, the total energy, is 1/2 an integral over the volume dr1, a second integral over the volume dr2. Okay, you integrate over the volumes, and now you can insert in place of the charges, you can insert the charge densities, rho of r, rho of r primed, okay, or sorry, r2 here, rho of r1, rho of r2. They are continuous variables now, but whenever you find a particle with a point-like charge, this density has a spike, okay? It has a peak. It goes to infinity if you are dealing with point-like particles, okay? So this is for point-like particles, but you can rewrite this equation here in the following way. So R1 minus R2 in modulus, okay? This is the same as that equation here, just that you are writing it as a function of the total particle densities. Okay, so uh, we can, of course, we have a 4 pi epsilon here because this is the electric constant of the medium. Okay, so we can show this just reduces to the potential energy of a set of particles. So this is the potential energy, the total potential energy. Okay, let us do the demonstration here. All right. So we have the total energy is equal to, we are dealing with classical point-like particles for now. All right. So we'll introduce the deltas in the representations of the charge densities, but this way we could have a very general charge distribution, which not only for point-like particles this can be used, all right? And we will see why this is important, this form of the total potential energy for interacting charges. So this way we insert here, we have 1 over 4 pi epsilon divided by R1 minus R2 in modulus. We insert here a summation over Qi. So there are two summations. We need to insert two indices. Okay, so let me rewrite it in details here. So we have a summation over I, Q of I, a Dirac delta of R1 minus Ri, and a second summation here runs for another index, Qj delta, Dirac delta of R2 minus Rj's, the indices of the particles, okay? And this is divided by R1 minus R2 in modulus, okay? So perhaps it is better to use another convention here for the moment, okay? Let me rewrite it as R and R primed, because in the discrete summations you could have R1 and R2, so let me rewrite it as an integral over dr and dr primed. This is R and this is R primed, okay? This is R and this is R primed, okay? So let us see what happens when integrating over these things here. What we have, integrating the first delta, it just ensures that you need to replace the r's by r sub I, okay? And the second integral is just the replacement of r prime by rj. So you will have 1 over 2, a summation over all the positions of the particles, point-like particles, qi, qj, divided by 4 pi epsilon, modulus of, because of this delta is just ensuring r is equal to ri here, minus this other delta when integrated is just ensuring that r prime is equal to rj. And this is the previous equation we already introduced, okay? So this is the Coulomb interaction between set of particles. They are pair interactions. So a particle I interacts with a particle J, and it depends on the distance between these particles, right? So you have a set of particles here. I will show it in the plane. So this is, for instance, some R1, there are some R2, some R3, and the particles Q3, Q1, Q2, and you sum over all the interactions between the pairs, okay? Particle Q1 interacts with Q3, interacts with Q2, and they interact with each other, and you sum over all, you add up all the potential energies. So this equation is equivalent to that, provided that for point-like particles, charge density of a variable r is equal to the summation over some discrete index I, qy delta, the Dirac delta of r minus ri, okay? So this is it. This is a general equation which just reproduces the total energy, the total potential energy of interactions between pairs of particles, all right? Now, let us, since this is demonstrated, let us remember the following thing. In quantum mechanics, a particle is described, so first quantization here, we are not second quantizing it yet. So in first quantization, a particle is described by a probability density. So the probability density is proportional to the wave function squared, all right? And we can write a charge density because it is proportional to where the particle is. So there is a probability of finding the particle at some point in space. This is a function of a position r, okay, it's modulus squared. So you have a psi dagger of R is not an operator yet. H psi of R in first quantization, this is just a function, okay? And the charge density would be given by the charge of that particle, which is a particle characteristic, okay, times the probability density of finding that charge at the point R in space. And notice that the product of charge, which is given in coulombs in the international system, times the probability density, which is measured in 1 over cubic meters, just produces exactly what we need, coulombs per cubic meter. Okay? So in quantum mechanics, we are willing to replace these densities here, charge densities, right, by probabilistic densities, by the modulus squared of the wave functions. And after that, we will second quantize the operator, all right? So this is it. But still I need to calculate another interesting issue in the classical field theory for the electrostatics, okay, which is consider the Coulomb potential, the electrostatic equation for the potential. So this is the electric scalar potential. It is given by the charge density here divided by epsilon. There is a minus here. This is the Poisson equation for electrostatics. But I am including a screening term. This is the screening factor here. We will see what it really mean. And now suppose we are using a green function formalism. Suppose you have a charge Q at a position 0. So this is a charge at the origin, point-like charge at the origin. Okay, so at r equal to 0, zero vector, the null vector, right? There is a particle in the origin of your coordinate system, and you try to solve the following equation. So the Laplacian operating on phi, which depends on the position of the particle, let us bring that factor to the left-hand side of the equation, minus alpha squared times phi of r is equal to minus the charge divided by the epsilon, which is a constant of your medium, all right? And there is a Dirac delta in 3 dimensions here. So this is a 3-dimensional Dirac delta function. So this is the equation we are willing to solve right now. Okay, this is the screened Coulomb potential, which we will arrive at, or if you prefer, it is a Yukawa type potential. So screened Coulomb potential or Yukawa potential, you can find these terms associated with the solution of that equation. So this term here, it corresponds to a mass term in an equation. Okay, so it is just a mass term here in the equation, but it will produce an exponential damping, as we will see. All right. So what we can do for solving this equation? Remember that the delta in 3 dimensions can be written as 1 over 2 pi cubed, the integral over the entire Q space. So there is a Fourier space which will index by the wave vectors Q, exponential of I Q dot R. All right. If you integrate that, you find the delta in 3 dimensions. All right. It doesn't matter if you pick up the plus or the minus sign here, but I will use the convention of a plus sign here. And of course, our phi of R, since I am using the 1 over 2 pi cubed for the Dirac delta, I can just define the Fourier transform by the following way. 1 over 2 pi cubed a phi in the Fourier domain here of Q times the exponential factor for plane waves over the entire wave vector domain. All right, we need to integrate over the entire volume in the reciprocal space, and we can insert this into the equation. And remember that the Laplacian acting on that will act only on this exponential, bringing a factor of second derivatives here, iq squared. Okay, so you differentiate twice, you will find out this factor twice in front of the equation. I'll will let you do the math, but this equation is converted into the following. Okay, if you insert these things here, it is converted into the following. So 1 over 2 pi cubed, an integral over d3q, the entire reciprocal space volume or wave vector volume. When you apply the Laplacian to that, we'll find out the minus q squared. So the q squared is just the dot product of q with itself because it is a vector. So this q squared here is just the modulus of this vector squared. We already have a minus alpha term squared there. So this alpha was already in the equation with a minus sign. This minus comes from the fact that you differentiate twice with respect to spatial variables, and this I appears squared. So I squared is minus 1. So minus q squared. A Fourier transformed potential. This is the Fourier transform of this potential. And the exponential appears here, which is equal to the minus 1 over epsilon, the electric charge, which is perhaps is not a good choice. I will use for the electric charge a capital Q. All right, so a capital Q is the electric charge of the particle, which is at the origin. All right, so replace the charge density by this thing here. The charge density here is charge capital Q delta 3 of R, and the delta 3, the Dirac delta in 3 dimensions of a vector R, it is just written in terms of a Fourier transform. It corresponds to taking the Fourier transform of the equation. So we can write this d3q exponential of iq dot r. Notice that the factors of the Fourier transforms can be cancelled out, and for the equation to be valid, since this factor is a common factor, both sides, we need that the integrand here is equal to the integrand there, okay, multiplied by the proper constants. And in this case, we have that minus q squared minus alpha squared times the Fourier transformed potential. This is the Fourier transform of this potential, which we don't know yet. It must be equal to minus the charge divided by epsilon times 1, because the integrand here has a 1 here. Okay, 1 over 2 pi cubed is common factor. The integration is in the same volume space. These exponentials are common factors. We can eliminate them, and therefore we find out what is the Fourier transform of the equation. The Fourier transform potential phi of q, it is equal to q over epsilon q squared plus alpha squared, because this minus sign cancels out this, and we have this is for the Coulomb potential, or the screened Coulomb potential. We have an alpha factor here. If you plug in 0 here for this alpha factor, you'll find out the unscreened Coulomb potential. But now our job is to calculate the inverse Fourier transform. So calculating the inverse Fourier transform, you have the following. Phi of r is equal to 1 over 2 pi cubed, okay, 1 over 2 pi cubed, integration over the entire space q here, charge divided by epsilon. They are just constants. We can move to the outside of the integral symbol here, times 1 over q squared plus alpha squared times the exponential I q dot r. All right, this is a plus I because we use that convention. But as a matter of fact, for second order equations, that doesn't really matter. If you could choose a minus sign, I'm just using the quantum mechanical convention here. All right, so this is a 3. 1 over 2 pi factor for each dq here. So this integral is over d3q, which could be used, one could use Cartesian coordinates, but it is better to use spherical coordinates, because this scalar product here, q dot r, can be written as modulus of the first, modulus of the second vector, which is just the distance from the origin, a cosine of theta. And this theta is just the angle formed by these two vectors. So you have q here, you have an r here, and you have a theta here. Okay, so they are the dot product of the two. The scalar product of the two is just the modulus of the first, modulus of the second, and the cosine of the angle between the two. So this could be written as q squared sine of theta d theta, or dq d theta d phi. So these are spherical coordinates in the space of wave vectors. And therefore, we can rewrite this equation, phi of r, this phi of r here. This is a distinct phi here. Okay, this is an angle, this is the potential. So this phi of r here is just 1 over 2 pi cubed. I can bring these factors outside of the integration. Integral over 3 variables. These integrals runs from q equal to 0 to infinity, theta from 0 to pi, phi from 0 to 2 pi. Okay, this is the usual convention for spherical coordinates. You'll have the q squared divided by this factor here. This q squared comes from the definition of the d3q, right? So q squared divided by q squared plus alpha squared, and the exponential we will write as I q r cosine of theta dq. There is a sine of theta because it comes from the differential here, sine of theta dq d theta d phi. All right, this is it. This is a triple integral which we need to solve. And the first thing we can solve is an integration over d phi, this phi here. This phi has no other dependence, so this integral just produces a factor of 2 pi, which cancels out one of these factors here. So we have phi of r is equal to 1 over 2 pi squared, because integration of this brings a factor of 2 pi, q over epsilon, and now we have a double integral of q from 0 to infinity, q squared divided by q squared plus alpha squared, all right? And now we can switch the variable, because here we have a cosine of theta, and here we have sine of theta d theta. And this is just a replacement of u is equal to cosine of theta, du is equal to minus sine of theta d theta. But now you reverse because for theta equals to 0, this corresponds to 1, the u variable. And for theta equal to pi, it corresponds to minus 1. So you can eliminate this minus sign of the differential, just switching the limits of the integral, and you have an integral from minus 1 to 1 of e, the exponential of I q u and du dq, all right? And we can perform this integral first, all right? This is what, so I was forgetting the r here. So I q r u. So we can directly integrate over the u. This integration is easy to perform first. And therefore, we have phi of r is equal to 1 over 2 pi squared q divided by epsilon, because this is just a constant, an integration from 0 to infinity of this factor here, q squared divided by q squared plus alpha squared, all right? And this integral brings two factors, e to the iqr, because when you integrate it and you insert the upper limit, you have e to the iqr, minus the inferior, the lower limit here, minus iqr, and this is divided by this factor here, iqr, okay? This is the integral now we need to perform, right? This is the integration we need to perform here, okay? But now this r is just a constant. This imaginary unit is just a constant, so we can rewrite it as the following: 1 over 2 pi squared I r q over epsilon. And notice this factor here is just even under the switching of the sign of the variable q. The variable q is a modulus. It is integrated from 0 to infinity. But notice the first term here, it is just e to the iqr, this q here from 0 to infinity, this term is unchanged. But the second factor, e to the minus iqr divided by iq, and this r is already here, we can switch the sign of the variable q, just eliminating this. We can bring it together with the minus q. And in the second factor, in replacement of the integration from 0 to infinity, we could integrate from minus infinity to 0. All right? Just switching q minus q to q and reversing the limits, and it's just a variable transformation. You can do that with a more calmly perform this demonstration, but it's just integration over dq from minus infinity to infinity, because we just switch the sign of the second factors here, and we have q, because q squared divided by this q here is just q here, divided by q squared plus alpha squared exponential of iqr, and this dq is already here. Right? So this is the integration we need to perform. We just, in replacement of integrating the second factor divided by q from 0 to infinity, we switch the sign. We change the sign of the second factor to a plus, but then the integration must come from minus infinity to 0, and the first factor is already from 0 to infinity, so we can bring them up together to find out this thing here. And now we need to use the residual theorem of Cauchy. So using Cauchy, we can use it. All right. So this variable is a real variable, but we can go to a complex plane. So this is a q. We need to integrate from minus infinity to infinity. If you close in an imaginary, so this is a real of q, right? In an imaginary axis or in a complex plane, so you go to a complex plane, you make an analytic continuation of this variable here to a complex variable, and you go from minus infinity to infinity in the real line, and then you close the path in the complex plane, which just involve a pole here. So we need to find out what are the poles of this function here. So q squared plus alpha squared equal to 0 produces two poles, which are plus I alpha and minus I alpha. So there is a pole here and another here. And when you close the path in the upper plane, in the upper half of the complex plane, you just pick up this pole here, and you need just to rewrite this factor here. So q squared plus alpha squared is equal to q plus I alpha q minus I alpha. Okay, and from the residual theorem, you just neglect the factor, this factor here, because the pole you are involving is I alpha, so this would produce an infinity divergence. So you eliminate that factor and you pick up this factor here, just replace q by I alpha. It is just a complex integration here, and therefore this equation becomes phi of r is equal to 1 over 2 pi I times 2 pi r charge over epsilon. I'm just rewriting this 2 pi and placing together the I factor here, because when you integrate this in a complex plane, you just make the integration in a complex plane here, in a complex plane, in some contour here in a complex plane is an anti-clockwise contour. You just need to multiply 2 pi I times the residues. The residues of this function is the function evaluated at I alpha, but just neglecting that factor. So I have here, I need to replace Q by I alpha divided by I alpha plus I alpha, so twice I alpha, which is just this function here, eliminating the pole there. And we need to replace this Q by I alpha, so I alpha R. And this is the result. Okay, this is the result of the potential. Now we have the following. Phi of R is equal to 2 pi I. It is cancelled out. I alpha is cancelled out. This factor of 2, multiply this. We have 4 pi. So we have the charge divided by 4 pi epsilon. And we can bring this R with this factor here. I times I is I squared. So you have a minus factor here, minus alpha R divided by R. Okay. This is the screened Coulomb potential. Okay. So what that does really mean? If you have alpha going to 0, this exponential goes to 1, and you have the full Coulomb potential. But in a material, usually in a solid state material, when you place a charge inside that material, for instance, an electron, it will drag close to it a cloud of positively charged particles, and when seeing from a certain distance, the electric charge will appear to be lesser than it is really. So this factor here, charge, the real charge times this factor here, takes into account the screening or the shielding of a given charge. If you place a negative charge in a medium, it will be surrounded by a cloud of positively charged particles, and this way it will seem to be less negative than it really is from a given distance. All right, so the charge is screened. The value of the charge is screened. And the factor alpha can be written as a function of some distance, a lambda of screening. So this lambda here, which is the inverse of this alpha, is called the screening length. Okay. So in free space, in vacuum, there is no screening. But in a material, in a solid state material, you'll have some screening of the potential produced by a given charge. All right. So what we have found out is that the potential phi of r equal to the charge divided by 4 pi epsilon e to the minus alpha r divided by r is equal in the Fourier transform domain to a phi tilde of q. So they are connected. They are this is the potential in real space r, and this is the potential in the Fourier transformed space. Phi of q is equal to uh, the charge divided by the epsilon q squared plus alpha squared. So this is it for the Coulomb potential with screening, all right, with the shielding of some shielding of the electric charge. Okay. So now let's go to a second quantized version of the potential energy, which is a two-particle term. Okay. So the classical corresponds to the following: U is equal to a, suppose, 1 over 2, okay, integral over d3r. Let me use 1 here now, okay, d3r2. So we have two integration spaces, the volume of charge density 1 and volume of charge density 2. The charge densities calculated at position r1, the charge density calculated at position r2. So notice that the volume differential times the charge density is just an infinitesimal point-like charge, and the volume 2 times the density at the position r2 is just an infinitesimal charge at the position 2, and this is divided by r1 minus r2, which is the distance. So we have here some dq1, this is the charge, all right? So this is the charge 1, which is equal to charge density at position 1 times the volume at position 1, and the other charge is located at some position 2, which is some dq2. It's an infinitesimal charge, a point-like charge. I am exaggerating here the differential, okay? But it's just a tiny, small volume here, which is equal to r, the density, the charge density at r2 times the volume d3r2 around this point r2, all right? So the distance between them is r1 minus r2 in modulus, okay? But now I can consider a screened Coulomb potential. So I will introduce here the exponential of minus alpha modulus of r1 minus r2, 4 pi epsilon here, because for charges, the energy is charge 1, charge 2 divided by 4 pi epsilon. And if the potential is screened, you'll have the exponential damping of that potential. All right, so this is classical. Now this is a classical equation for the potential energy with screening. Okay. Now let me do the following. Just remember that equation. Okay, it will be important. And this is the Fourier transform of this expression here. And this r here is the distance between the charge producing the potential and the charge feeling that potential. So this r here is the modulus of r1 minus r2, all right? Now let us do the following. Remember that in first quantization, as I mentioned, first quantization, you could replace the charge densities at r1 by the electric charge. Let us consider now electrons. Okay, so they are electrons, and the electric charge of an electron is minus E, which is minus 1.6 times 10 to the minus 19 coulombs in the international system. All right, so this is a minus E psi, the complex conjugate of that function, calculated at R1 times psi at R1. Okay, so this charge density will be the modulus squared of the wave function in quantum mechanics in replacement of the classical charge distribution. But now we will second quantize it. We will convert these two things in second quantized version. For second quantized, we will convert this into operators. Okay, so we'll convert it into operators. And therefore, we will have U, which is the total potential energy, which will become an operator. We will have a 1/2, okay, just to overcome the double counting of the potential energy. So this is 1/2 is necessary. And integration over the volume R1 and integration over the volume R2. I will plug in here the form of the potential, so R1 minus R2 in modulus. This is a screened potential. 4 pi epsilon is just a constant, which corresponds to the constant of the interaction. R1 minus R2, if they are just point-like charges, the charge of the first particle is minus E times the charge of the second particle, which is minus E. So we will have a electric charge. Let me write it as a Q. All right. Well, Q is not a good. Is not a good. Is not a good symbol here. But do not be confused by this exponential here. This E is the electric charge, and this E, I guess it's clear. This E is the Euler number. Okay. So we have here minus E times minus E. So let me write it as a capital Q squared. Okay, so this capital Q here is the electric charge squared. So it will avoid confusion here. And therefore, we can rewrite it in the following way. We can just bring to the outside of the integrations the constants. But now I need to insert the probability density here, the probability densities for the electron at position 1 and the electron at position 2 as operators. So we would naively to write psi dagger as an operator of R1 times psi dagger of R1 as an operator, and here psi dagger of R2, psi of R2, okay. But from the recipe we described it in the previous lecture, we can switch the positions of the dagger operators. We can switch, but if we switch these two, we have a minus sign because this is a fermion. So when we switch these two factors here, we can switch this with the last term here because they are fermions for electrons. And in this case, it is better to rewrite in the following way. So in replacement of this thing here, we write psi of R1 dagger, psi of R2 dagger, and here we just switch it, the psi of R1 with the psi dagger of R2, it will bring a minus sign here, but we can eliminate that minus sign if we switch these two. So the R2 becomes in front of the R1, and we have this expression here in second quantized form, all right? And we can rewrite it in the following way. 1 over constant, 8 pi epsilon, the charge squared. So notice they are electrons here. So there is a repulsive energy if you are dealing with distinct charges, all right? For distinct charges, electrons and protons, the sign of the potential energy for the Coulomb interaction will become a minus, a negative sign. And it means when the potential energy is negative, the interaction is attractive. If the potential energy is positive, it means it is repulsive. So we are dealing with identical particles, therefore they must have the same charge in this case for electrons. Okay, there are some weird things happening when you deal with electrons and the anti-electrons, which are positrons, but this is beyond or outside the scope of this lecture and this course. But for the same type of particles, the identical particles, which are in this case electrons, they have the same charge, and you have a repulsive energy. So if in the classical world the energy is positive, is greater than zero, you have repulsive interaction. But if you have a negative energy, it is attractive. Attractive interaction. Okay? So the constants are outside of the integration symbols over the volume 1, R1, over the volume 2, R2 in 3 dimensions. And we have now to calculate the following. Psi dagger, R1, R2, e to the minus alpha modulus of R1 minus R2 divided by the modulus R1 minus R2 here, okay? Psi of R2, psi of R1, okay? So this is the second quantized form of our operator. Notice this object here in the middle of your sandwich, okay? This is the classical potential apart from some constants. This is the classical potential between two particles. Then you need to integrate over the volumes and insert densities. But in second quantized form, they will be operators. And you need to calculate that. All right? So this is Coulomb potential in second quantized version. Now, let us do the math. Okay? Just remember, a psi at the position R1, if you are dealing with a continuous variable R, you need to divide it by the square root of the volume, right? Because in position space, you are integrating over volumes, and therefore you need to have this energy in electron volts or joules or whatever the units of energy you are using, but you need to have a density, which is psi dagger psi dagger psi. It is a density. It must be measured in cubic meters. So of course these operators, when multiplied, must produce 1 over volume. So the normalization will be 1 over the square root of volume. a summation over, so the k we are considering a discrete set of plane waves, okay? But whenever we need to go to a continuous, we can replace summations by integrals, right? And we will need to do that in a while, briefly, all right? So summed over is C dagger K, oh, CK, sorry, CK sigma for electrons, CK sigma e to the I K dot R. So the variable R is continuous. So the psi of R1 we can write that way, right? And of course, psi dagger is just the transpose conjugated of that equation. And therefore, we can rewrite our operator in the following way. Q squared divided by 8 pi epsilon. Square root of volume comes from here. We have 1 over volume squared. All right, we will have 1 over volume squared in this case, because there is an integral over this volume, over this volume. There will be 2 volumes here, so we need to have 1 over the square root of volume multiplied for every term here. And we'll have a double integral and 4 summation terms. So I will have summation over K1 sigma 1, a summation over K2 sigma 2, a summation over K3 sigma 3, a summation over K4 sigma 4. All right? Why is that? Because there is a summation from this, summation from this, summation from this, and summation from that term. There are 4 terms, so 4 summations. What is not position dependent, so the operators here are not position dependent, we can bring to the in front of the integrals, and therefore we have a C dagger K4 sigma 4, right? So the index 4 comes from this, a 3 comes from that, C dagger of K3 sigma 3, the spins of the particles, okay? A C of K2 sigma 2 is not a dagger because it's an annihilation operator here. A C of K1 sigma 1. So in this case, we are just annihilating first the particle with wave vector K1, then the K2, and then creating the K3 sigma 3 and creating in the end the particle with K4 sigma 4. This is what we are doing. And now, so the constants are here. Now we are left with the integrals. Okay, the integrals. So there will be an exponential factor, a plane wave factor for this, a plane wave factor for this wave function or operator. So there are 4 plane wave factors, and there are 4 spinors coming from this, coming from that, coming from this, coming from that. And this needs to, at a certain point, to match the spins. Okay, so the spin of the particle 2 and the sigma 2 and sigma 3 spin indices must be the same, and the spin indices of 1 and 4, or just combinations of spins. But of course, you have to conserve angular momentum and all that. And in this way, what is left here is multiplication for integrals. And it is a double integral here over the volume. So let me write it here. a double integral over dr1 over dr2 volumes. Okay, from this equation comes an exponential of minus I k4 vector dot r1, which is the position, and k vector comes from here. So I can just erase it here. An exponential of minus I k3 dot r2, all right, because this factor here. We can rewrite the potential factor exponential of minus alpha r1 minus r2 divided by the modulus r1 minus r2, all right? And then from that operator comes an exponential of I. Notice they are complex conjugated. K2 dot R2, and this exponential I to the K1 dot R1. All right? So this is what we need to integrate. This is a very complicated expression, but notice we can switch variables, we can change variables as a matter of fact. We can rewrite R2 equal to, suppose, R, or, sorry, we can rewrite this R1 minus R2 is equal to R, all right? We can make this identification here, and therefore, from this, we have R2 is equal to R plus R1, right? And the volume integral over R2 becomes, if you fix the R1, becomes an integral over D3R, right? So it is just a switch, a changing of variables here. So you just replace the integral over R2 by an integral over R, but just if you fix the R1, because in the integral for R2 it is a constant, and now you are just changing the variables, you'll find out the following. Q squared divided by 8 pi epsilon 1 over volume squared here, summations over the indices 1, 2, 3, and 4. Let me write it just in a compact notation. C dagger of 4, C dagger of 3, C of 2, and C of 1, meaning that 4 is the set of labels, 3 is this set of labels, 2 is this set of labels, 1 is this set of labels, okay? And the summation of over 1, 2, 3 means spins and all the variables here. So now the double integral becomes an integral over dr1, an integral over dr, and if we replace R2 by R plus R1, we will find out exponential of minus I K4, or let me write the R1 in front of that. R1, what we will find with R1? So a minus in front of everything, K4, K3, minus K2, because minus minus you'll get a plus here, minus K1, because minus minus you get a plus, and this is multiplied by R1. So this is what we have for the D3 of R1 here, okay? And what is left is the exponential of minus alpha R in modulus divided by R, because this R1 minus R2 is just the modulus of this. In modulus is just the modulus of this factor. Now we have the form of the screened Coulomb potential here. And what is missing? We have an exponential of minus I K3 dot R plus K2 dot R. So we have I to the K2 minus K3 dot R. Right? I hope we didn't forget anything, because this calculation is very tricky here. So we can say this is a K vector, this is a K vector, a Q vector, sorry, a Q vector. And this Q vector, notice when you integrate out dr1, what you find out, Q squared over 8 pi epsilon, a volume squared here. Integrating this exponential, we'll find out the 2 pi cubed a delta. There is summations over 1, 2, 3, and 4 indices. C dagger of 4, C dagger of 3, C of 2, and C of 1 indices. Remember, they are K4, sigma 4, K3, sigma 3. So these indices, 4 is, remember, is K4, sigma 4, and you need to remember that. This becomes a Dirac delta in momentum space, K4 minus K1, and if we define K3 or K2 minus K3, we define it minus K, all right? This is a Dirac delta in the following form. So K3, K4, we define it as some Q, but for now you could just write a K3 minus K2 here in this Dirac delta, because you are integrating this dr with this exponential. Notice that now the integrals are split, and the integral over R1 is not mixed with the integral over R. But the integral over R, okay, the integral over R of this factor here is just the Fourier transform of this object. So what we have, we need to insert 1 over 2 pi. Sorry, we don't need to insert anything, because this is the definition of a Fourier transform here in this space. We will have something like this. A 4 pi needs to be taken from here. So we let here a factor of 2. And the Fourier transform of that is a 4 pi times. That's why this 8 pi here is cancelled out in favor of a factor of 2. And we have 1 divided by this number here, Q squared plus alpha squared. When we integrate out this D3R here, we just arrive at this factor, which is the Fourier transform of the screened Coulomb potential, right? So remember, this vector Q is just K2 minus K3. And now we can integrate, but just to integrate over, for instance, you could integrate the 4 indices here. You have a summation over K4 and sigma 4. The sigma spins, it doesn't matter. But for the summation over the wave vectors here, you need to replace the summation by volume divided by 2 pi cubed and integral over d3k. And this cancels out this factor here over 2 pi cubed, which came from this delta, the integration over dr1. And therefore, when we do that, we can replace K4 by K1 plus Q. Right? When we integrate this delta, we cancel out one of the volumes. We cancel out the factor of 2 pi cubed, and our result is the following. Potential energy, or the second quantized version of this operator, is the charge squared twice the epsilon times the volume. This 2 pi is just eliminated from the whole equations, and we integrate over the variables 1, 2, 3, and the spin of the fourth particle. Okay, so the spins, there are spin indices, but for the momentum, we have a C dagger of K1 plus K, a C dagger of K3. I am omitting spin indices here, deliberately omitting spin. K2, K1, okay, K3, K2, K1. We already integrated that, converting the summation over the fourth index into an integral, which cancels out this and cancels one factor of volume here, and it is divided by q squared plus alpha squared. Right? Now we can convert the, remember, K2 is equal to, or K2 minus K3 is equal to this Q here, and therefore we can rewrite the K3 equal to K2 minus this K here, and we can replace the summation over K1, K2, and K3 by summations over K1, K2, and this Q here. And therefore, our final form of this operator will become U equal to Q squared divided by twice epsilon times the volume, right? A summation over K1, K2, and Q, okay, and Q, which corresponds to the Fourier Transform variable, C dagger of K1 plus Q, C dagger of K2 minus Q, C dagger of K1, or K2 here, sorry, and C dagger of K1. All right. So this momentum here is transferred from between the particles when they interact and they scatter. Right. This is the form, and the proportionality corresponds to this Fourier transformed potential, which for the case of the electromagnetic interaction, it is just the propagator of the photon in this virtual photon in this case. So when we look at this, sorry, here is not dagger, here's annihilation operators. When we look at this form here, what we have Feynman diagrams for that, all right? So Feynman diagrams. And we can write, suppose you have a particle K1 in the beginning of the process, but you are summing over So for a specific, let me write a momentum 1 of the particle 1, electron 1. You have an electron and you have another electron, P2, and the momentum exchanged by these particles is the photon momentum cubed, or is just a virtual particle. It's not really observed in this case, but we represent it as some Q which is being exchanged by these two particles. So here emerges the particle P2 minus that H bar K, okay, minus. So you annihilate the particle P1, you annihilate the particle P2, which corresponds to this operator. But then you create in this point here a particle with momentum P2 minus H bar Q, which is this wave vector here. And after all, you create this particle, the final particle with momentum P1 plus H bar Q. So in this graph, this Q is a positive, and or it could be negative, of course. So in this graph, the particle 1, the particle 2 is emitting a momentum to the particle labeled 1, and momentum is conserved in this process. Okay, so this is the Feynman diagram for this process. But since you have summations over K1 and K2, perhaps this operator, because it is summed in the interaction process here. Suppose you have a definite value for the momentum P1. Okay, this P1 here can be annihilated by the first of the operators here or by the second of the operators here. You don't know what, because here you are summing over all the possibles. When you say a specific value for momentum P1 here, this particle, initial particle, can be destroyed by this operator or by that operator here. And therefore, you have a second graph, and since you need to switch you need to just permutate the symbols, permutate the actions, and they are fermions, you have a minus here. A minus in the second graph, if you would calculate the action of these operators on a specific initial state. So suppose the initial state is P1 and P2. You don't know if this operator is annihilating this factor and this is annihilating that, or the other way around. In this case, you have that a P1 particle is being annihilated in this position here. I'll switch here, the initial states. You could do that for the final states, all right? But as a matter of fact, you would have a a second this factor of 2 here can be cancelled out uh, because there are summations here. So this came from preventing the double counting of the energies, and of course this corresponds to the so-called exchange of final or initial particles here. Okay, and this momentum here exchanged in this process will be distinct from the momentum exchanged in the final process. Okay, well, so far so good for the Coulomb interactions. I am finishing this class here because it, it is becoming too lengthy, and I guess in the end your attention is being lost to other subjects. But to finish this this thing, just remember, or let me say that the probability of scattering probabilities are proportional to something like the modulus squared of this interaction here. So you have a P1, P2 initial state, P3, P4 final states. The modulus squared of this interaction will become a proportional, it is proportional, or this scattering cross section, the differential scattering cross section, usually it is used the letter sigma. Do not confuse with spin. So this is for scattering. It is proportional to that object here. And this thing here is proportional to the charge squared. So you have a charge to the fourth power because you are just colliding two electrons divided by the epsilon of the medium squared. So this is proportionality factor here, which comes from all the calculations. And you'll find out something like 1 over q squared plus alpha squared squared. All right, when you collide the two particles. In that graph, you are exchanging a q here. Okay, so you have a P1, P2, a final P3, and a final P4 here. You have particles. They are exchanging momentum. The two electrons, they are colliding. And the scattering cross section is proportional to the modulus squared of the Hamiltonian to second order because the interaction occurs in the two particle operators. Okay, and in this way, if alpha is equal to 0, which corresponds to unscreened case, okay, this transferred momentum corresponds to something like one of the electrons, P1 or P4 is equal to P1 minus Q or plus Q, whatever, minus or plus, depending on the sign of the Q, right? And therefore, what you have is here you can calculate, for instance, Q could be P4 minus P1 or P1 minus P4. It depends on the signs, right? And in this way, here, remember that momentum is proportional to velocity, so mass times velocity. And in the case of elastic scattering, the modulus of P1 is equal to the modulus of P4, right? And you have here a factor which depends on momentum to the fourth power, and you could find something which in the non-relativistic case, it is a approximation of the Muller scattering. And you can plug in here. So you have to calculate something like this: 1 over q to the fourth power, which is just modulus of momentum p1, or momentum p1 minus the momentum p4 modulus to the fourth power. You can calculate that, all right? And I recommend you to look at the book by Greiner and Reinhardt. Greiner, Reinhardt, Field Quantization. Discussions of these two particle operators in the context of non-relativistic theories are around pages 55 to 74, I guess. And you could also take a look at the book by Kittel, but not the introduction to solid state theory, the quantum theory of solids instead. Quantum theory of solids. Okay? Take a look in this book, chapters 5 and 6. It is a good reference for just supporting what I told here. Okay? Well, I'm finishing here. Hope you can find it useful and see you next time. Bye bye.